Greetings, students. Today, we embark on an exploration of a fascinating problem from LeetCode titled Merge K-Sorted Lists. In this challenge, we are tasked with merging multiple sorted linked lists into a singular, cohesive sorted linked list. Imagine that you have an array of linked lists, each elegantly arranged in ascending order. Your mission is to combine these lists while preserving their inherent order. To illustrate, consider the following input: three linked lists containing the elements 1, 4, 5, 1, 3, 4, and 2, 6. The goal here is to produce a new merged linked list that seamlessly integrates these elements into a single sorted sequence. The expected output would be 1, 1, 2, 3, 4, 4, 4, 5, 6, where we meticulously select the smallest values from each list in succession. As we delve deeper into this problem, we will uncover elegant strategies to achieve this merging efficiently. Let us proceed with this intellectual endeavor. A min heap is a tree-based data structure where each parent node has a value less than or equal to its children. This means the smallest element is always at the top or root, making it easy to access the minimum value quickly. Because of this property, min heaps are perfect for priority queues, where we process elements based on priority rather than their order of arrival. In a priority queue using a min heap, the element with the highest priority, which corresponds to the lowest value, is served first. This characteristic is crucial for algorithms like Dijkstra's for shortest paths and prims for minimum spanning trees. Min heaps allow for efficient operations, with both insertion and deletion happening in logarithmic time, or O log n. This efficiency is vital when dealing with dynamic data sets, ensuring quick updates and retrieval of the smallest element. Typically, a min heap is implemented as an array where navigating through the parent-child relationships is straightforward with simple index calculations. For a node at index I, the left child is at 2i plus 1, and the right child is at 2i plus 2. When adding or removing elements, we maintain the heap structure through a process called heapifying, which ensures the min heap property remains intact. This systematic organization enables efficient priority management, making min heaps a foundational element in modern algorithm design. The code snippet here demonstrates how to use a min heap to solve the problem of merging k-sorted lists efficiently. We start by importing the heapq module, which provides us with the functionality to manage a heap. In the min heap priority queue function, the first step is to create a min heap from our input list using heapq.heapify elements. Think of a min heap like a priority queue where the smallest element is always at the front, making it easy to access. Next, we enter a loop that runs until our heap is empty. Each time through the loop, we use heapq heappop elements to remove and return the smallest element from the heap. This element is then added to our result list. Finally, once all elements have been extracted and added to the result, we return the sorted list. This method ensures that we efficiently merge all k-sorted lists into one sorted output by continuously pulling the smallest available element. The merging technique for sorted lists is an essential process in computer science that allows us to combine two or more already sorted sequences into one single sorted sequence. Imagine you have two sorted lists of numbers, like a stack of cards neatly sorted in ascending order. Instead of shuffling all the cards together and sorting them from scratch, we can simply look at the top card of each stack and pick the smaller one to add to our new stack. This method takes advantage of the fact that the lists are already sorted, which makes the merging process much more efficient. Instead of spending time to sort everything again, an operation that generally takes O(n) log n time, we can merge them in linear time, O(n), where n is the total number of elements in both lists. To achieve this, we maintain pointers for each list, keeping track of our position. By comparing the elements pointed to, we can decide which one to add next to our merged list. This continues until we've gone through all elements, resulting in a fully sorted combined list. This technique not only saves time, but also minimizes the number of comparisons needed, making it a highly efficient solution for combining sorted data. Let's take a look at the function merge sorted lists, which combines two sorted lists into one sorted list. First, we initialize our pointers, I for list 1 and j for list 2, and create an empty list called merged to store our results. The goal here is to compare elements from both lists efficiently. In the first while loop, we check if there are still elements to compare in both lists. If the current element in list 1 is smaller than the one in list 2, we add it to merged and move the pointer I forward. Otherwise, we add the element from list 2 and move j. Once we finish comparing elements, we have to handle any leftovers. The next two while loops do just that. If there are remaining elements in list 1, we append them to merged, and then we do the same for list 2. Finally, we return the fully merged sorted list. This method is efficient and ensures that we maintain order as we combine the lists, making it a great example of the merging technique. The problem at hand is to merge k sorted linked lists into one sorted linked list. Let's break down the steps to tackle this effectively. First, we need to understand our data structure. We have an array containing k linked lists, each of which is sorted. Each linked list node has a value and a pointer to the next node. Next, we initialize a min heap, or priority queue. This handy structure helps us efficiently retrieve the smallest element among the heads of the linked lists. By inserting the head of each list into the heap, we can always access the smallest current node quickly. We also create a dummy node to serve as the starting point for our merged list. This simplifies our logic when appending nodes. While the heap isn't empty, we extract the smallest node, append it to our merged list, and check if there's a next node in the same list. If there is, we push that next node into the heap. Finally, once the heap is empty, we return the merged list starting from the dummy's next node. This method has a time complexity of O(n) log k because we process each node once and perform log k operations on the heap for each node. Remember to handle edge cases, such as empty lists, as you implement this solution. In this problem, we are tasked with merging k sorted linked lists into a single sorted list by splicing together their nodes. The challenge lies in efficiently managing up to 10,000 linked lists, with a total of up to 10,000 nodes across all lists. Additionally, each node's value ranges from -10,000 to 10,000. These constraints will significantly influence our approach, particularly in terms of time and space complexity, as we devise a suitable merging strategy. The provided Python code solves the problem of merging k sorted linked lists into one sorted linked list, which is a common challenge in algorithm design. At the heart of this solution is a min heap implemented using the heap queue module. Think of a min heap as a special kind of priority queue that always lets us quickly access the smallest item. First, we define a list node class. This is our building block for the linked lists, containing a value and a reference to the next node. In the merge klists function, we start by creating an empty list called min heap to serve as our priority queue. Next, we add the initial nodes from each of the k-lists into the heap. Each entry is a tuple containing the node's value, its index, and the node itself. This structure helps us maintain the order based on node values. The algorithm then enters a loop that continues until the heap is empty. In each round, we remove the smallest node from the heap and attach it to our merged list using a dummy node to simplify the process. If this node has a next node, we push that successor back into the heap. This method ensures we handle every node efficiently, achieving a time complexity of O(n) log k. Here, n is the total number of nodes, and k is the number of lists. Using a min heap is essential, as it streamlines the selection of the smallest element, which is crucial for merging sorted structures. Overall, this approach combines clarity and performance, showcasing effective algorithm design. The time complexity for merging k-sorted lists is O(n) log k, where n represents the total number of nodes across all k lists. To understand this, think of a min heap as a tool that helps us efficiently find the smallest element among these lists. Each time we insert or extract an element from the min heap, it takes log k time because we're managing k lists. Since we perform this operation for each of the n nodes, it results in a total complexity of n log k. Now, regarding space complexity, it is OK. This is because, at any given moment, we only need to store up to k elements in the min heap, one from each of the k-linked lists. The space used for the final result list, which depends on n, is not counted in this space complexity. By focusing on these elements, we ensure our algorithm remains efficient while handling multiple sorted lists. Understanding these complexities helps us appreciate the effectiveness of our approach.